Module 26 to 11, Control Systems and Fundamental Concepts. Part 2.0.0, Relays. Identify and explain how to troubleshoot various relays. Identify and describe control relays. Identify and describe solid-state relays. Identify and describe overload relays and their classifications. And explain how to troubleshoot relays. Here's a highlight right out of the gate. A control relay is an electromagnetic device that's used to control various circuits. Contactors are used to switch power circuits with high current loads, like the circuits that serve large motors. Relays are used to control circuits to switch relatively low current loads, thus their contact electrical ratings reflect the difference. Here's a highlight. A maximum current load of 15 amps at 600 volts AC is common, although there are some exceptions. Some relays also have much lower ratings. Contactors generally have from 1 to 5 poles, all of which are typically connected to individual sets of normally open contacts. While relays have multiple poles too, those with just 1 or 2 poles are very common. However, relays far more likely than contactors to have poles with multiple positions, such as the one shown with more sets of single-pole double throw contacts. So here's auxiliary contacts. And I think they're showing us that 1314 is an auxiliary contact on this contactor. Relays are used to control circuits of magnetic starters, contactors, many other devices. There are hundreds, if not thousands, of relays from forms and styles. The traditional magnetic relay is still very common, although the use of solid-state relays continues to increase. So here's a highlight. It says some relays are designed to provide circuits and equipment protection. For example, thermal overload relays protect motors, controllers, and branch circuit conductors against excessive heat. Other types of electrical protective relays include overcurrent protection, both time delay and instantaneous overvoltage and undervoltage protection, directional overcurrent protection, percentage directional differential protection. I've seen phase loss monitors, which are relays that will turn off a circuit if you lose one of the phases in a 3-phase circuit. The operating characteristics of these protective relays are all similar and are covered in this module. However, their individual settings, adjustments, and actuating functions are quite different and are beyond the scope of this module. For specific instructions, always consult manufacturer's literature. Control relays. Control relays are electromagnetic devices that handle relatively small current loads. Be used as a pilot device to control contactors that handle much larger loads. Relays differ in voltage rating, current rating, number of contacts, contact convertibility, contact accessibility, and a host of other characteristics. Relays can also amplify contact capacity when properly applied. So here's a highlight. It says standard control relays are limited to 600 volts AC due to the difficulty of maintaining sufficient distance between the conductive components internally to prevent arcing. Relays that manage higher voltages are available, but they're very rarely encountered. So the wiring diagram in figure 9 and 10 demonstrate how a relay amplifies contact capacity. So here we have a control relay. And this control relay is controlled by a temperature switch. When this temperature switch, when it gets cool enough and this closes, then the control relay is energized and it closes this normally open contact, closing the motor starter, and then the motor starter starts the motor. So here we're using a very small amount of current to control this motor contactor that controls the larger current of the 3-phase motor. Notice how this is normally closed, held open. And then in figure 10, they have a thermostat that's normally open, held closed. So you'd have to heat up a room in order to close this one. Where this one, you'd need something to cool off to a certain point in order to actuate it. So here they're using a separate circuit. It's a 24-volt source to control this control relay, and then the control relay is going to turn the motor starter on and start the motor. So this is a 240-volt three-phase, three-wire motor, and they're using 24 volts to control this motor rather than using 240 volts through the control relay. Instead of having a 240 volt control relay using the power from the motor, you can use a 24 volt control relay. All right. It says, did you know how? All right, what's the did you know? Thermostatic switch symbols. Figure 9 shows a thermostatic switch at the top of the diagram. Note that the bar on the switch is angled up with the coiled portion below it. Now look at the thermostatic switch at the bottom of the diagram in figure 10. Note that the switch bar is angled down. The difference between the two is important to the sequence of operation. All right. Let's see here. The switch in figure 9 closes on a fall in temperature. The coiled portion of the symbol represents the bimetal component that bows in one direction or another as the temperature around it changes. It contracts when it's cooled, which would make a good switch bar fall. In figure 10, the way the symbol is drawn represents a switch that closes on a rise in temperature. Figure 11 shows a control relay being used to multiply the switching functions of a push-button switch. In this circuit, a single pole push-button contact can control the operation of a number of different loads, thanks to an interposing 6-pole relay. So here's my control relay. We have a simple, momentary, normally open on switch, and there's a normally closed off switch. When you push this on switch, it energizes the control relay, closing this holding contact, controlled by the control relay. So it becomes normally closed, and the energy bypasses the on switch so that you can let go of it. It'll go back to its normal position of open, but you still are feeding this control relay, and it's controlling these other 5 loads. A starter, a pilot light, a contactor, a solenoid, a timing relay. Notice how when we energize the control relay, we energize the starter. We de-energize this pilot light. So if that pilot light is red, the red light goes out. And the contactor also is being de-energized. I don't know what the contactor is doing, but whatever it's controlling, it's no longer, it's turned off. And then it also turns on a solenoid, and it turns on a timing relay. We don't know what these things are doing in the real world, but we know that they're being controlled by that control relay. Relays are also commonly used with complex controllers to sequence and control many interrelated operations. Programmable controllers supervise and provide logic, while the relays direct the electrical traffic and make the required connections. Figure 12 shows some of the examples of plug-in relays, which are popular and flexible in their application. I should have looked it up. This is the base of a relay, and the relay itself is wired toward on this wiring diagram. One of these should be normally open, and they're not showing us which one. I think 4 is normally closed, and 3 is normally open, and I think on this one 6 is normally open, and 5 is normally closed. 1 and 8 are the commons, and 2 and 7 are the power operating the relay. So here's a couple of different, what we call ice cube relays. They're cubes, and they're clear plastic, so we call them ice cube relays. Here's an 11 pin, no, what's this one? 14 pin. This is 8 pin, and this is also 8 pin. These round ones go in there. Notice that there's a key, this little slot, so that the relay can only be plugged in one orientation. You can't put it in wrong. The key has to line up with this indent. So that'll keep it from being plugged in wrong. Timing relays. A timing relay has a contact that are repositioned at a specific time interval after the coil is energized or de-energized. An on relay refers to a delay in contact movement after the relay is energized. An off delay refers to a delay in contact movement after the relay is de-energized. A timed function is useful in applications such as the lubricating system of a power generating turbine, in which an oil pump must deliver lubricant to the bearings for a set time before the turbine begins to rotate, usually about 30 seconds. Fossil fueled furnaces also incorporate fan delays to avoid blowing cold air into the space when the system starts. This allows time for the heat exchanger to warm up first. A lot of times, if you have a conveyor system, you want the conveyor to start operating before the hoppers open and start dumping product on the belt. Also, at the end, when you push the stop button, you want the hoppers to close, but you want that belt to continue running. If you have 2,500 pounds of gravel on a belt, uh, conveyor belt, you'll never be able to start it if it stops with all of that gravel on the belt. When you push the start button, you're going to burn the motor up trying to move that much weight. So what they'll do is they'll put a delay on de-energize on the conveyor so that when you push the stop button, the conveyor continues to operate for 30 seconds and it dumps all of that product off of the belt before it comes to a stop. So these are just ways that you can use timing relays. Solid state relays. A solid state relay is another option in switching applications. Solid state relays are available in different styles and ratings, including time delay versions. They have no moving parts. An electronic switching device with no moving parts or contacts. And again, here's our base with a key. And here is a blown up view of the bottom of the actual relay itself with the key. So this key has to line up with this hole in order to be able to put this 8-pin base or relay into the base. You'll notice from the key, this is 1, 2, 3, 4, 5, 6, 7, 8. So over here from the key, we'd go 1, 2, 3, 4, 5, 6, 7, 8. It's a mirror image because this relay is going to be turned over and plugged in. So the 1 will end up over on the left. And again, I 1 is common and 8 is common. And I believe 3 is normally closed and 6 is normally closed and 4 is normally open, or I don't remember, to be honest with you. I don't know which one of these is normally open. I think 4 and 5 are normally closed and 3 and 6 are normally open. They usually draw it with the arrow not touching the contact bar. If the arrow were drawn up here not making contact, then you'd know that 6 is normally open and 3 is normally open. But right now my mind's not working, so I can't remember which it is. But anyway, one common use for a solid-state relay is the input-output track of a programmable controller. A solid-state relay can be used to switch a 120-volt AC signal to a 5-volt DC signal. The advantages of solid-state relays include the following: no moving parts, resistant to shocks or vibration, well sealed against dirt and moisture. Control input voltage can be isolated from the relay controlled circuit. So the following are some typical solid-state relay control circuits. Power transistors for DC loads. As shown in figure 14A, a power transistor is used to connect the load to the line. This is an opto-isolated relay with a light-emitting diode connected to the input or control voltage. It's a common circuit arrangement in solid-state relays. Those that use this coupling method are referred to as opto-isolated. Optical is light, isolated. So this would be an LED. I'm sorry, this would be the LED as the control input comes in. This light emitting diode would emit light on this opto transistor. This transistor operates when light hits this optical eye. It allows current to flow, and the current will flow through the base of the transistor, allowing current to flow from the emitter to the collector, and it turns on the load. Basically, it's isolating it from the back plane of the PLC. Again, this one is using a triac instead of a transistor, but the same opto-isolated feature is here with an LED and an optic eye looking for light. This is a reed switch. It uses magnetism. So the control input creates an electromagnet that pulls this reed switch closed, and it allows this triac to fire and power the load. Triac controlled AC relay. A triac is connected to the load in place of a power transistor. This circuit also uses an LED as the control device. When the photodetector sees the LED, it triggers the gate of the triac and connects the load to the line. And the reed-controlled AC relay, as shown in Figure 14C, you can control solid-state relays and AC circuits using a small reed relay to control the output. In this circuit, small sets of reed contacts are connected to the gate of the triac, and the control circuit is connected to the coil of the reed relay. When the control voltage sends current through the coil, the magnetic field produced around the coil of the relay closes the reed contacts and activates the triac. So this is a highlight. The reed relay uses magnetism. The reed relay uses magnetism. All right. Control voltage of most solid-state relays ranges from 3 volts to 32 volts. Triac-controlled relays commonly have load voltages rating of 120 volts to 240 volts with current ratings between 5 and 25 amps. All right. Well, let me read this. Some solid-state relays incorporate a zero switching feature. Basically, they don't turn off until the sine wave falls back to zero. This means that if the relay is programmed to turn off when the AC voltage is in the middle of the cycle, it'll continue to conduct until the AC voltage returns to zero before it opens the circuit. That way it's not opening under a load, under a lot of current. When it gets back to zero, the current falls to zero. It can disconnect the circuit without a lot of arcing or sparking. Overload relays. To protect a motor and its related circuits from accidental or prolonged overloads, either the starter of the motor or the motor should be equipped with an automatic protective device that will open the circuit. This protection may be provided by fuses, circuit breakers, overload relays, or a combination of devices. Overcurrent protection must be provided in every motor circuit, but additional protection is best provided in the form of a magnetic overload relay. They're used in both manual and automatic motor starters. So some of them have a bimetallic strip. Basically, it's two dissimilar metals welded together that change shape when they are heated or cooled. So the current of the motor is going through this heater and going back to the motor. And if it gets too hot because of too much current flow, it will open this circuit and it'll turn off the starter, the motor starter. It will trip, and then it has to be manually reset before you can start the motor. Heater element is sized based on the full load current of the motor. The resistance is carefully matched to a current range that produces a specific amount of heat. More current generates more heat, which causes the overload relay to open. Most modern overload relays are thermally operated and consist of two strips of metal bonded together. That's the bimetallic, two metals, bimetallic switch. Both have a different rate of thermal expansion. When the bimetallic, there you go, two metals, bimetallic strip is heated and deflects sufficiently, it mechanically opens the overload relay contacts. This in turn de-energizes the coil of the contactor and the motor is de-energized. And they have to be manually reset. Motors can become overloaded due to a problem with the driven machinery, such as a failed bearing in a compressor. A failed bearing in the motor itself can also be the cause. A motor can also exceed its rated current due to low line voltage or loss of phase in a three-phase system. This is often referred to as a single phasing a motor. So it's a three-phase motor, but you lost one of the phases, and it continues to run on just two of the three phases. So they call it single phasing. All right. Overload relay operation, a schematic for a basic motor starter shown in figure 16, and a manual starter. Overheated thermal elements trip a mechanical latch, forcing the starter contacts to open and disconnect the motor from the line. So here are your heaters, and if too much current goes through them, they get hot, and the bimetallic switch opens this overload contact, and it disconnects the power to the coil, so you unlatch these contacts that were feeding the motor. Okay. Fuses versus overload relays. Fuses are not the best choice to provide overload protection. Their basic function is to protect against short circuits. Motors draw a high inrush current when starting, and conventional single-element fuses have no way of distinguishing between this temporary and harmless inrush current and a damaging overload. If a non-time delay fuse is chosen based solely on the motor full load amps, it'll blow every time the motor started. On the other hand, if a fuse large enough to easily pass the starting current is used, it may not provide proper protection. I'm not going to say may, I'm going to say it definitely will not. It will not provide the overload protection needed by that motor. So, overload relays have some interesting characteristics. One is referred to as an inverse time trip feature, permitting them to both hold the current load as the motor starts and accelerates, yet providing protection if even a small amount of overcurrent is sustained. So dual element time delay fuses do provide a measure of motor overload protection, but are non-renewable. A motor starter is easily reset after it trips. Overload relay classifications. Overload relays can be classified as being either thermal or magnetic. Magnetic overload relays react only to the current expressed and are not affected by temperature. These are good if you're using a motor starter in a warmer climate, hot room. As discussed previously, thermal overloads relays rely on the rising temperatures caused by excessive current to trip the overload mechanism. Thermal overload relays, though, can be further subdivided into two types: melting alloy or bimetallic. We already talked about the bimetallic. Melting alloy heater element and solder pot are shown in figure 17. Motor load current passes through the heater element. When it produces too much heat, it melts the alloy. So it's got like a solder inside of this chamber. There's a solder in here, and when it's hardened, this wheel will not turn. This is a ratcheting wheel, and it will not turn when the solder is hard. If too much current goes through this heater, it'll melt that solder, and it'll allow this wheel to spin. So you have a spring loaded bar that's stuck on the teeth of the ratcheting wheel, and it's holding the contacts closed as the motor is operating. And if there's too much current going through the heater, then the solder will melt. That's what they call it, a melting solder, a solder pot. It'll melt, allowing this wheel to turn, and that spring will go past the wheel and open the contacts and shut off the motor. And it cools off relatively quickly. 10-15 seconds, you're good to go. You can reset it, and you can once again use those overloads. Melting alloy thermal units are interchangeable and often can offer one-piece construction. This ensures a constant relationship between the heater element and the solder pot, and always allows for factory calibration. They're virtually tamper-proof in the field. Many types of interchangeable thermal units are available to provide precise overload protection for any full load current. All right. Bimetallic overload relays, though, have two major advantages. First, available automatic reset features desirable when devices are mounted in locations that are not easily accessible. Second, bimetallic relays can be field adjusted to trip within a range of 85 to 115% of the normal trip rating of the heater unit. This feature allows turning of the operation to best protect the motor while avoiding unnecessary interruptions. The ambient temperature does affect the heater element of overload relays. Ambient compensated bimetallic overload relays were designed to address this issue. Motor starters with overload relays are often installed in a different environment than the motors they control. If the ambient temperature around the overload relay varies too much and is often hotter or colder than the motor environment, a standard thermal overload design will not respond consistently. All right. Electronic overload relays. Newer motor starters are often equipped with electronic overload relays. Electronic models offer a wider range of settings and increased versatility. Electronic overload relays depend on current transformers to monitor the current and respond accordingly. Current flowing through the conductor induces current in a winding that surrounds it. The level of induced current reflects the true current flow, informing the overload relay of the operating conditions. So electronic models more accurately identify excessive current and phase losses, and they consistently react with greater speed and reliability than traditional models. Overload relay selection. Here's a highlight. When selecting thermal overload relays, the following factors are considered: motor full load current, the type of motor, the difference in ambient temperatures between the motor and the controller. Motors of the same horsepower and speed do not all have the same full load amps. The nameplate of the motor to be protected must always be checked to obtain the specific full load amps. This is the most important factor in selecting the heating element. Thermal unit selection tables are generally based on the full load amperage of the continuous duty motor with a 1.15 service factor and operating under normal conditions. All right. Troubleshooting. Here's a highlight. It says the solenoid coil is usually designed to function as long as the voltage remains within 80 to 110% of its rated voltage. So the solenoid coil will operate to within 80 to 110% of the rated voltage. This allows it to compensate for common variations in the voltage. At a lower voltage, the magnetic field may not be strong enough to move the armature. At higher voltages, the coil may overheat when it's energized for a prolonged period of time. When sufficient voltage is applied to the coil, the magnetic field builds quickly and the armature closes with a snap. The contacts then reposition sharply as well. Internal binding due to wear may cause a relay or a contactor to make and break sluggishly. This may be encountered in relays that rarely operate. Periodic testing to best ensure they operate properly when called upon. All right. I can't go back to the drawing or the picture of the contacts, but the contacts they're rounded. They're not flat on the top. They're rounded, and that allows the two of them. Yeah, I can't make my other hand curved. Those two curved surfaces allow this to make in a lot of different positions because these things are moving. They don't always come right back to the exact point where they were last time they made. So they might move a little bit. And the roundness of them allows them to make contact in a lot of different positions. If they were flat, you could get a little bit of a gap in there. You could get a little bit of debris, and it would keep them from making contact. But the rounder ones, they always make good contact. And they actually even, there's a tiny little arc when they make or break, and that tiny little arc melts the surface of the contact, and then it solidifies back to that nice round feature. So they're kind of self-repairing in a way. They'll do this thousands of times before it actually becomes a problem with pitting and burning and what have you. They can last for a very long time before the contacts have to be changed. So I'm not going to go over this whole table. Yeah, this table is about troubleshooting. You'll want to kind of read over it and have an idea of what needs to be done in order to troubleshoot a motor starter or a contactor of any sort. All right. Section 2.0.0, section review. A single pole push button contact can be used to control multiple loads using a what? Type of relay controlled by a magnetic field is, all right. The type of overload device that requires a cooling off period before it can reset. And the solenoid coil of a relay is typically designed to work properly at what percentage of the rated voltage. All right. Okay, I'll stop here and I'll see you on the next video.